kind of a basic definition, is the sharing of electrons between atoms of similar electronegativity. Who wants to put a definition to electronegativity? Sure.
It's kind of how tightly an atom holds on to its electrons. Like oxygen is a greedy bitch, so she holds on to her electrons really tightly. And then hydrogen not so much, and that's why water's polar.
I love it. I love it. Exactly. It's a relative measure of, how much you either are holding your electrons or you can attract even more electrons to you. How much can I get even more electrons, or how much am I willing to give up my electrons? I don't even need them. I don't even care. Okay? And so covalent bonding is generally going to occur between things that have somewhat similar electronegativities. And so, in fact, they're willing to share with each other. And you have, for example, here, this is CH4. We have carbon, so we have this s orbital here, has 2 electrons in it. Our p orbital wants to have 8 to be in sort of a low energy state. Carbon only has 4, okay? But if it shares with 4 hydrogens, each with 1, it can sort of fill this shell. Most of this should be sort of like intro gen chem review. I won't go into more detail than this. If you need more information, let me know, and I can point you to some resources. Okay? But the biological molecules of interest in our class are almost always going to consist, everything's pretty much carbon-based. We're made of carbon. So we're going to be looking primarily at stuff that is linked covalently. Okay, so electronegativity, a measure of an atom's ability to attract electrons to itself. Fluorine, our most electronegative atom, it really wants to get an extra electron. It only needs 1 to fill its outer shell. Over on this end, this is stuff that's willing to give up its electrons. So ionic bonding is then a bond distinct from covalent that's occurring between a positive and negative ion. It requires actual electron transfer. Okay, so there's some large difference in electronegativity required for this type of bonding to occur. An example would be salt or sodium chloride, NaCl. Na by itself is unstable. Chlorine is also unstable by itself, but the sodium cation, where it has given up 1 electron, is very stable. The chlorine anion, once it has received 1 electron, is very stable. And then these two can interact with one another and form an ionic bond. And so again, stuff that's far apart will be able to participate in ionic bonding. So here we have a plot. We have potential energy in kilojoules per mole on our y-axis, and on our x-axis we have internuclear distance in picometers. Okay, so this is between 2 atoms coming together. We're looking at interatomic energy. Okay? So when these things are really far apart, they're basically not interacting at all. Okay? As they get closer together, they're going to exert a force on each other. Initially, this will be an attractive force until we reach some ideal point, okay? Some interatomic spacing that is idealized, and as you push these 2 things even closer together, they'll now exert repulsive forces on each other. They're just literally in each other's space. Okay? So the force can be attractive kind of over longer ranges. The force can be repulsive over shorter ranges. And there's some distance where the forces will be exactly balanced. Okay? Or net force will equal 0. And this is going to be our interatomic spacing, or when these 2 things are bonding to each other, our bond length. So this one here is an H2 bond. The bond length is 74 picometers. Where's my mouse? Okay. And we have this sort of lowest energy point. Things want to be in the lowest possible energy state. Okay. Things are considered energetically favorable when they're at the lowest possible energy. It takes energy to get out of here and either pull them apart or push them closer together. Okay? So as they come together, eventually they'll hit a spot where I'm happy, I'm bonded, this is exactly the lowest energy, and if you want to pull us back apart or push us closer, you need to put energy in to make that happen. Okay? Energy balance of an attractive and repulsive terms give us the minimum energy. Okay? So this is sort of a minimum on this plot. If you were to take the derivative, okay, of your energy curve, you would get a force curve. And what you would find is that, what's the minimum? What's the derivative at a minimum like this? 0. So if you see a plot that is force versus interatomic distance, this is where on this side we're going to have negative slope. This side will have positive slope. Here you should be crossing the 0 point on the force graph. Okay? I don't know that I have a force graph in these slides. But again, the forces will be balanced. The forces will be crossing the 0 mark. The energy will be at the lowest. Another thing I kind of want to point out here is that we have sort of this negative potential energy. Right? So actually, when the numbers are less negative, it's a higher energy, it's less stable. Try to kind of wrap your head around the negative sign there. Okay. So here we have our hydrogen-hydrogen bond. Okay. You might be provided a table like this on your homework to do something with or use these values. They're slightly different, as you can see, because I took these from 2 different resources. So the bond length at 74 picometers is the same. The energy is slightly different. 432 versus 436 kilojoules per mole. Okay. Picometers, kilojoules. We're talking about per mole because if we were actually talking about the joules for just like one single bond, we're talking about really, 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 really tiny amounts. Okay, so we're going to talk about if we had a mole of H2 bonds. Okay. These are positive values here. What this means is this is the amount of kilojoules per mole needed to break that bond apart. Okay? So really quickly, just because I got to repeat it over and over and over again, does it take energy to break a bond? Okay, so when I break a bond, do I release energy? No. No. And this is something that is sort of counterintuitive and students get wrong. If we just isolate a single bond, okay, I have a bond, there it is. I break it apart, I have to put energy in. I do not release energy on the breaking of that bond. When I make a bond, I release energy. Okay? So like I said, it's kind of the opposite of how you may have memorized it once upon a time. It's kind of counterintuitive. Making a bond releases energy. These 2 things want to do this. Once they bond, they release some energy. Getting them back apart requires putting energy in. Okay? And one of the places where I think this becomes a problem is ATP, breaking off one of those phosphates into ADP. We go, oh, that's the energy of the cell. We release energy. We get energy out of that experience, but it's because there are a whole bunch of other things around, namely water. And all of the hydrogen bond changing that's happening is really what makes the net a release of energy. The single breaking of that phospho bond or phosphoanhydride bond, that bond alone takes energy to break it. Okay? So just beat that into your head right now. Breaking a bond is energy in. Making a bond is energy out. Okay? But we're never in a vacuum. We're never talking about a single bond, and that's how things get a little more complicated. Okay, so what I would like you to do now, there will be a question that appears at the bottom of the screen. Since I'm not doing attendance and I'm not doing participation officially anymore, you're free to just not answer this question, but I strongly recommend you do it. So maybe turn to the person next to you or a group of 3 and sort of work through this. One of the feedback I got last semester was we did this, I collected them for participation, and then I didn't give them the answer until the next day. They really hated that. So we will do the answer after, but take 5 minutes and talk about this with the people around you. So the question is, which bond is more energetically favorable? In other words, which one is more likely to form and harder to break? And your choices are carbon-carbon or carbon-hydrogen. Okay, so you can use the table. That's where you'll get this answer. Then I also recommend sketching out an energy versus distance curve for these 2 bonds. Okay. And so a scale that looks something like this that goes from 0 to negative 500 kilojoules per mole and 0 to 200 picometers will be sufficient. Okay. And then I will say, I think, definitely on one of the homeworks and also on the exam, there was something very comparable. I just picked different bonds and asked you to do something similar. So good practice. So take a couple of minutes, talk with the people next to you, and answer these questions and sketch this up.